Hello, welcome to Math 27 post-election recording. So we will continue with the discussion today. It's recorded. Some of you are attending, and yeah, so that we can have a Thursday meeting dedicated for some wrap up and review and uh, pointers for the exam. I decided to do this lecture today. So these are the goals for this. Roughly the bullets for the goals. So today we are going to learn improper integrals, the second type, with infinite discontinuities, and we will also go with applications, areas and volumes. For areas, just like area bounded by curves, and for volumes, we have like two like washers and this method, and this one, and the other one is shell method. We will discuss them one by one as we go on. So let's have first our improper integral. So last time we get the improper integral with limits like this and like here and like here. And then we have discussed this and maybe this one. And also we have started improper integral on, I remember I had given you an example wherein we get this integral. X minus 2. And then here, this is the second type. There's a discontinuity at x equal to 2. And it is happening at the end, one of the end part, one of the limits of integration here, specifically the lower limit of integration. And we learn that this integral converges. When we say it converges, this has a limit. It converges to 2 square root of 3. And we say that the integral converges if there's a limit, and diverges if it has infinite, or it is divergent in the sense that we have a divergent before. So today, let me begin with an example on the second. I will leave the other examples to you for reading, and of course, I have made it sure that it will be enough for you to pass the exams. All right. So the second example is the following. You get the integral of this function, 1 over x raised to 3 dx. Note that sometimes I put dx here, this part, dx, and then sometimes here, but it's just a matter of notation. The first step is, the question here, is it convergent? Okay, we know that here, if we get 0 in the denominator, we have 1 over x raised to 3, so it's not just the ordinary definite integral. So the first thing to do is to write, to find the indefinite integral. In this case, the indefinite integral is the following. It's just x raised to -3 plus 1, and then -3 plus 1. Of course, plus c. This is x raised to -2 over -2 plus c. So that means this is just -1 over 2x squared plus c. Now, that's your here. We write this as a limit ng integral from 0. Here we get b. and then 2. Your b approaches 0. And then it is defined at the right of 0, so it's 0 plus. Okay. Why 0 plus? Because this is the discontinuity is in the lower limit of integration happens here. It's 0 plus, and here it's 0. It's from the left. Just write everything again. So this is a lim b going to 0 plus, and then 1 over 2 negative x squared, and then 0, and then b. Or not b. It's 2 here, and then here b. We just have to plug in this one. It's just the limit b going to 0, and then negative 1 over 2 squared, 2 squared minus negative, so magiging positive 1 over 2b squared. Okay. This one here goes to negative 8, negative 1/8. This one here, as you approach b very, very small, this one here goes to positive infinity. And thus our answer for this is positive infinity. And this means this integral, specifically this improper integral, what? Diverges or is divergent. Diverges, or you can say it's divergent. So that's our answer. All right. So now here we have discontinuity at x. Here we get f is equal to, this f here is 1 over x raised to 3 has discontinuity at x equal to 0. Now let us look at the example, which is just the extension of our first example here. We get negative 1 to 2. Oh no. Negative 1 to 2, and then 1 over x raised to 3 dx. So solution, our function here given by 1 over x raised to 3, the same as above, has discontinuity at x equal to 0. And then your 0 is between 2 and negative 1. Wait. Negative 1 here and 2. And therefore, because it's inside the interval of integration, I mean, this is between the upper and lower limit of integration, what we shall do is to break this down into two integrals. It's 0 here, so we write this negative 1 to 2 dx over x raised to 3 by the property earlier of integrals. We get negative 1 to 2, then x raised to 3 plus, not 2, but 0 here. Okay, let me erase. 0, and then from 0 to 2 of the following. And now we can solve this individually. This is your B, this is your A. Okay, remember that we already did B. So here, 0 to 2 dx over x raised to 3 above. So from above, this is 0 to 2 is divergent. When one of the components is divergent, we can say that the entire integral is divergent. So thus, what can you say about the entire integral? The entire integral is the integral from negative 1 to 2 is already divergent because whatever happens at the other one, you get plus infinity, so it's divergent. So you don't need to solve for the other one when one is divergent. You can conclude immediately that the entire integral is divergent. So now before we go to the next topic, let me go to an important note. Note that it is important to realize the discontinuity. So for example, warning on applying ordinary integral in the sense that what I mean ordinary here is the just the definite integral on improper ones. So this will give you a wrong answer. For example, this integral from -1 to 2 of the following, the example that I did earlier. So it's just -1 over x squared. And then we have 2 below. And then if we have -1 to 2 here, we just have -1 over 8. And then plus 1 over 2. So you get here 3 over 8. So this is wrong because there's a discontinuity, infinite discontinuity at x equal to 0, which is inside 0, for which no, let me phrase this next. 0, and this 0 is between the lower and the upper limit of integration. So don't apply the ordinary technique for the usual integrals when your integral has discontinuity on the between or inside the interval of integration. In this case, the interval of integration is -1 to 2, and 0 is between them. And 1 over x raised to 3 has discontinuity at x equal to 0. Okay? Naririnig ba?
Yes po, sir.
Okay, thank you. So now we go to areas. Madali lang yung area natin. So last time, we know that if we get here a function and this is interval A and this is A to B, and then this is your function y equal to f of x. This is your y-axis and x-axis. The area here is given by the integral from A to B of our function. And then the bounding function below is just y equal to 0, which is the x-axis. Now we would like to generalize this into areas between curves. But before that, let me like do an example in here. So here, if you get 1 to 4 of square root of x, this is interpreted as getting the area of this one from 1 to 4. And then this is your graph here. Y is equal to square root of x. And then this is the area. Let's say the area is A. Then the area is just equal to this integral. In case you are not asked to solve, don't solve. But if you are not you are asked to evaluate, then just evaluate. This is just the integral from 1 to 4 of x raised to 1/2. And then x raised to 1/2 plus 1 is 3/2. And then we have here, and then 0 to 4. Thus we get, you can have 2/3, and then 4 raised to 3/2 minus 0 raised to 3/2. Okay, so this is just The answer here is over 3. This is 14 over 3. But in case your answer is just 2 over 3 and then 14, no, 4 raised to 3 halves, it's already okay for me. All right. Now, let me generalize these two areas between curves. And we have 2. And then we have a requirement that if we have f and g continuous on the interval a to b. And then here, we will restrict that our g of x is less than or equal to your f of x for all the x inside the interval a to b. Then the area, this is the integral from a to b of f of x minus g of x, parenthesis, with respect to x. This one is the area between of the region between f and g from a to b. So if we have a graph of that, and this is your x-axis and y-axis, you get here y is equal to f of x, the bigger function, and y is equal to g of x, the lower function. And if this is your interval, a and then n with b, then this is your a sub r. So this is just f of x minus g of x. Now, yeah, that's it. This is a sort of a height function. Your somewhat height here is in terms of let's call this height. This is the upper function or the greater function minus the lower function on that interval f of x. Of course, it should be f and g should satisfy this relation for the entire interval. In case it doesn't satisfy, then you can interchange the position depending on which is greater and which is smaller, and then dividing the area, I mean the interval of integration. And of course, you can do this for y, and then the same. Okay, if we have here our functions of y, and then continuous on c and d, and then f is also in terms of y here. This is for all our y inside interval c to d. Then the area of the region is just equal to the integral c to d of f y minus g of y dy. The picture here is as follows. You get x and y axis, y, x, and then you get here. Our convention is the leftmost is more positive. So we have here y is equal to it. No, it's a function of x. X is equal to here we get f of y, and here we have x is equal to g of y. Then we have here the bound. So this is c and d, and then this is the area given by this formula. Sometimes it's in here you do horizontal strip. This is horizontal strip. Because you are getting the area of the individual strip here and then summing it all together. Here we have vertical strip. For vertical strip, in area, you get here dx, and here, and here you get dy. Okay, because this is a strip, this is your change in y, so this is dy. Okay. So let's proceed now with a few examples. So it's the first example is the following. It's easy because the graph is given very suppose R is bounded by your equations, y equal to 2, y equal to root x, and then x equals 0, x equal to 2. So if you draw that, this is your x-axis, your y-axis, y is equal to 2 is this, and then x is equal to, y is equal to square root of x is something like this, and then x equal to 0, this is just this one, and then x is equal to 2, this is just this line. So the integral that will give you the area here of the region is the integral from 0 to 2. The upper function is 2, the lower function is root x, and then with respect to x. So here we look at this as our height area element. This is the vertical strip, and then this is your dx, and then this is your upper and lower. So the height is upper minus lower, so 2 minus root x, and then everything here is in terms of x. Any question?
None po, sir.
Yeah. Hello? May tanong?
Wala po, sir.
Thank you for responding. Okay, sometimes your graph is not easily the intersection or the upper and lower limit of integration is not given, and it's just implied by the situation or like the scenario given in the problem. So for example here, I ran out of slides. Sometimes it's easier to do it in the vertical strip or dx as a variable of integration. Sometimes it's easier in the dy, but of course, sometimes you're not also given the upper and lower limit of integration. Okay. Okay, let's do this in our next example. So our next example is the following. R is the region bounded, BDD bounded by y is equal to x squared, y is equal to root x, and here we get no bounded limit upper, let's say boundary points. It's just like not so formal term. Boundary points are given. So what you will do, of course, is to graph this equation. I mean, these curves. So let's graph this. This is your y-axis, your x-axis, and then the graph of x squared is just this. The graph of square root of x is just this. This is y is equal to square root of x. This is y is equal to x squared. That means if you get a vertical strip, when you use dx, vertical strip, I mean, strip first. Pag vertical strip, ano yan, dx. So using vertical strip, first we are to find the intersection. And then later we will also use horizontal strip. So find your intersection. So this is the intersection of these two are the points where the two functions are the two curves are meeting. So y is equal to x squared. So the first one is x squared. The second one is root x. If you square both sides, you get x to the fourth is equal to x. Of course, you know that when x is equal to 0, they are the same, but there's other solution. So what we will do is you put it this way, equal to 0. And then x raised to 3 minus 1 equal to 0. And then from the graph, we know that there are only two intersections. The one is x is equal to 0, and then the other one is x raised to 3 minus 1 is equal to 0. Over reals, it's not factorable. So that means this is just x is equal to cube root of positive 1. So this is just 1. So this is 0, and then this is x equal to 1. Okay? Of course, if you plug in here, we get y equal to 1, 2. So for the first one, when you are using vertical strip, the area of the region here is given by upper function, which is square root of x, and the lower function is x squared. Put parentheses with respect to x, and then we integrate from 0 to 1. Okay? All right. Now, for the horizontal strip, okay, you get when y is equal to x squared, this means your x is equal to the positive square root of y. Y positive, actually it's positive and negative, but we are only to take positive because the negative one is on this side. Okay, and then the other one is y is equal to square root of x. Then this means that x is equal to y squared. Okay, so this is your upper now. Okay, let me draw this. And then we integrate from 0 to 1. So in the area using dy, so area now, the integral, put parentheses, 0 to 1 still. But now everything is in terms of y. So this is your upper. This is associated with x squared. This is square root of y minus the one associated with y is equal to square root of x. So here, this is your lower. This is just that one. Okay, so that's it for our area between curves. Now, sometimes there are curves that intersect between the interval that you're integrating. So suppose your R here is bounded by y equal to sine x, y equal to cos x, and then x equal to 0, x equal to pi over 2. And then if you do the graph, there's an intersection. So the graph looks like this. This is your graph of sine, and then this is your graph of cosine. It starts with 1. Sine starts with 0. This is your, okay, this is your 0. And then there is an intersection. So this is pi over 2, and it intersects at pi over 4. Now, this is area region 2, area region 1. So this one is y is equal to cosine x. This one is y is to sine x. And then this is your x-axis, your y-axis. Now the area total is just the area of the region 1 plus the area of region 2. For the region 1, it's just the integral from 0 to pi over 4 here. And then upper is cosine minus lower is sine. And then with respect to x plus the area of region 2 here is from pi over 4 to pi over 2, and then the upper now is sine, and then the lower is cosine of x with respect to x. So now here we see some breaking of our region into two sub-areas, so sub-regions, I mean. Okay, that's it. So now let's go to our sample that we will use vertical and horizontal strip. And then we will proceed with volumes after this. Okay. So this one, if you use x as a variable of integration, that means a vertical strip. You get the area, divide the region into subregions, namely specifically two subregions. Okay, here is the region. R is bounded by y equal to square root of x, y equal to x minus 2, and x-axis. X-axis as equation y equal to 0. Okay. So remember this example. So y is root x is the graph here. And then y is equal to x minus 2 is when y is equal to 0, x is equal to positive 2. So you get here 2 and then this. Okay, so this is your region. Now, notice that if you have this as our upper function, we break this down into two subregions, so region 1 and region 2. Because here, this is your upper function and this is your lower function. Here, this is your upper function and this is your lower function. So it differs. So this is 0, 2, and then here we get, what is this point? So what is this point? Let us solve for that. So square root of x is equal to x minus 2. And then x minus 2 squared is equal to x. So you get x is equal to x squared minus 4x plus 4. So here we get 0 is equal to x squared minus 5x plus 4. And then we get x minus 1, x minus 4. So x is equal to 1 and x is equal to 4. We know that when x is equal to 1, somewhat like here, but it's not included in the region. We cross this out. This means this is x is equal to 4. We will use this one. Okay? Now, the area of the region is equal to area of region 1 plus the area of region 2. So here we use verticals. The first is use vertical strip. And then we will use horizontal strip later. So this is the area of region 1 is area from 0 to 2, and then parentheses, dx, and then upper function is, this is the upper function, and this is your lower function. So square root of x minus 0. And then the other interval is from 2 to 4. Upper function now is the same, square root of x for the first one. And then the lower function is minus, but don't forget the parentheses, x minus 2 dx. So this is now the area using vertical strip. Now it's easier when you use horizontal strip. So let me redraw the region here. This is 2, this is 4, and this is 4. When this is 4, this is y is equal to x minus 2. Then this is 2. And this is y is square root of x. This is your region. Now, this implies that x is equal to y squared. And this implies that x now is just y plus 2. If you get our horizontal strip, my drawing is somewhat not exact. Okay. Yeah, this is your horizontal strip. From if you travel from here to here, the bounding upper bound function is this. If you travel from here to here, the lower bound function is the same. So it's just one integral. So the area now of the region is just the integral. In here we will use dy, and the integral from 0 and then end with 2. And then upper function is associated to this line. It's associated, it's this. So this is just put parentheses, minus, and minus what? Minus y squared, which is this. Remember, when you have y here, all here are in terms of y. Okay, so I think that's it for our area bounded by two regions. Don't forget my examples. And of course, we will do review examples on the coming review session. So I think it ends my discussion on area. Okay, a 1 minute break, and then we will go to volumes. Okay, let's continue with volumes. Here we will consider volumes of solid of revolution. Here the concept, if we have an area, say this area, and then you want to revolve this about an axis. So here, example, this is our axis, and then we revolve this, you get something like this with hole inside. So suppose this is your axis, and then this is from A to B. So this is your generated volume. I will not be discussing like much of the conceptual build up here. I'll directly give the formula. So the first one is disk. So the concept of this here is, of course, we will set this in x as variable of integration, but the same happens when y is your variable of integration. So here you get the disk. What is a disk? A disk is, of course, like you have small, the area of the volume of the disk is just delta x times this height. And then I mean this area. And then this area is pi r squared. And then this is your r. So we will do that here. Now suppose you get this, and then you want to revolve this about the x-axis. So revolve this, and then you get a strip. Then you get here a mirror strip, and then this will become like a disc. Okay, this is your disc, and this is your r. And we know that area is pi r squared, so the volume of the solid is just the volume is pi, and then r squared, r is in terms of this function. Okay, let me write this in variable r, function r, so to emphasize radius. And then we will start from a and then end with b. A to b dx. Of course, when you have y as variable of integral, the volume is from c to d pi r of y squared dy. Okay, that's it. Example. This is easy, like just plug in formula. So we get graph of this y is equal to cosine of x. And then we have the region, of course, the axis, this axis should be should not intersect, should not pass through R. Region R can be tangent, like touching R only at just the line, but it's not passing through entire R. For example, what I'm trying to say is if you have this region and the axis of revolution should be here, or should be just tangent, or if this is a square, then at one side only. It's not passing here because you get double counts. So when we have double counts, it's not considered in the scenario or the situation that we are dealing with. So here, our region is bounded by this curve, this y equal to 0, this is x-axis, and y-axis. Y-axis is x equal to 0. And then first is revolve about letter A, x-axis. Let me check my notes first. So in case you are curious, this is given sometimes in the, so the intersection is pi over 2 and 0, and 0 here, and we get here 1. Okay, first revolve about the x-axis and then about the y. So for about the x-axis, you have this graph, and then it's going to be like this if you revolve. Okay, this is your resulting solid. And the volume is given by 0 to pi over 2. And then what's our formula? Pi. And then what's our radius? This is cosine of x squared dx. This is the answer. And then letter B here about y-axis. So the resulting solid will be like this. So this is your curve. And then you revolve this about here. Then you get something like this. Okay, so this is your y and this is your x. Now the volume will be just from 0 to 1 and then dy. But here, what is your x in terms of y? So x here is r cosine of y, right? Just r cosine. So that's it for our, so here our bounds is from 0 to 1, here from 0 to pi over 2. Okay. Now we will go to washers. So for washers, you get, I will situate this in x as variable of integration, but it's the same for y. So here we get two curves here, and then the other curve is here, and then this is, suppose this is A and this is B, and we're going to revolve it about x-axis, about some arbitrary, say x equal to no, so suppose we want to revolve it at x-axis. You can revolve it at any suppose x equal to in this case x-axis. This is your x-axis. And then this is y is equal to, say, d. And then the volume will just be pi. And then you put a, d. And then this one is the outer radius. And then squared. And then this one here, change color, is ri x minus inner radius squared dx. Of course, you can do the same for y. If you have y, then v is equal to pi c to d ro of y squared minus ri of y squared dy. Let's go to an example. I'll extend a little bit. Maybe I'll just finish up to Shell's method. Okay, example number 1. So this is a book example. So the curve is the following. The bounded by negative x squared plus 4 and y is equal to this is from the module negative 2x plus 4. So if you're going to graph this is the graph. And then we want to get the intersection. So this is negative 2x over 4. And then you get this one. This is not to scale. This is y is equal to negative x squared plus 4. And then the other one, the inside is y is equal to negative 2x plus 4. And then the first is we revolve this about x-axis, y-axis. Note that for shells, here, no, washers in this, the strip are perpendicular to axis of revolution. Okay, that means if this is your axis, you revolve here, the strip is perpendicular to this axis. Okay, so here, this is your region. First is about the y-axis. So we will revolve this about here. And then, of course, if we revolve that about there, you get a strip which is perpendicular to the axis of revolution. So this means that your x is 4 minus y, but you just get the positive because it's at this part here. And then here you get x is equal to 4 minus y over 2. So this is your out, r out. This is your r in. So the formula to get the volume, so the resulting volume will for letter A is the following. You just have this, and then there's a hole inside, and then can you imagine, like, then this is it's something like a hat, but there's a conical hollow left inside. The volume is the following: pi, and then we start from This is here we get 2 and this is 0, 0 to 2. Y2 because when y is equal to 0, negative x squared plus 4 is equal to 0. That means x squared is equal to 4, and then means x is equal to plus or minus 2, but the plus 2 here, minus 2 here, so just consider the plus. Okay, and then the outer r is, and then put here, the outer r is here. This is square root of 4 minus y. The inner r is 4 minus y over 2. Okay, so this is now your answer. The next is to revolve this about the y is equal to negative 2. Okay, now it's now here, negative 2. So you revolve the entire thing here. So the volume, so this R outer, and then this is R inner. Let me change the color to emphasize. So R outer is from here to here. R inner is from here to here. So this is R O R I. Now for R outer, this is just this square root of 4 minus y minus negative 2. So minus negative 2 is magiging minus minus 2. And then the R inner is 4 minus y over 2 minus negative 2, or magiging plus 2. Thus, the volume will just be pi, and then we start from, what is this point here? The same pa rin. This is from 0 to 2. Oh, wait. It's not, it's x is equal to 2. 0 to 2. And then just the same. But what about letter C? Y is equal to negative 2. So y is equal to negative 2 is here. So you get something like this. And this is y equal to negative 2. And you have something like this one, and then there's a hole inside. So this is your, I'll emphasize, this is your R outer, and then this is your R inner. So your R outer is just, this is in terms of x, because our strip should be perpendicular to the axis of revolution. So R outer is negative x squared plus 4 minus minus 2, so plus 2. And then R inner is negative 2x plus 4 minus minus 2 is plus 2. And then you get the volume now will be 2 pi, not 2 pi, pi. And then from here we get from 0 to 2. Let me repeat this one. Since you are looking at y, this is this one here is 4. So instead, I get a mistake here. Instead of 2, it's supposed to be 4. And here also it's 4, because it's y. We're running our variable y, so y from 0 to 4. So in this case, ito naman yung 0 to 2. And then your R outer is just copy. that's it. That's it for our. So here we did revolving about x axis, about y axis, about the line parallel to the y axis, and there about the line parallel to the x axis. I made a mistake here, 0 to 4, but I rectified. So because here we start from y equal to 0 and end with 4 for our horizontal strip. Here we get from 0 up to 2 because here 0 and here is like x is equal to 2. Then we run from there. This is our strip perpendicular to the axis of revolution. Okay. All right. Now, sometimes it's hard to, okay, I'll extend a little bit to finish the method of shell. It's hard to express y in terms of x. For example, this is method. For example, we have here like this graph given by 2x minus x cubed. Solve for x. It's hard. What we will do is to use different method. So in this case, you have a shell method. So this is the formula. Volume is just 2 pi. And then the shell we get, it's r of x times h of x. And then dx, of course, starts from a to b. All right. Of course, it's the same for horizontal strip. Now we will illustrate this in the original example that we have. So suppose this is your example. It's hard to get y as function of x here. So we want to revolve this about the y-axis. This is your region bounded by y is equal to 2x squared minus x raised to 3, y-axis, and the x-axis. So in this case, we will get a strip. In this case, strip are parallel to axis of revolution. The strip is parallel to the axis of revolution. This is your axis of revolution. This is your strip. And then what we do is to revolve it here. And the formula is 2 pi. Start from 0. And then we end here at, what is this end part? So to solve for the intersection, you get 0 is equal to 2x squared minus x raised to 3. So you get x squared and then 2 minus x. Equating to 0, this implies x is equal to 0 and x is equal to 2. So this is the intersection 0 and 2. And then for this strip here, you get the radius or the distance from the axis is r of x. And then the height is this. The radius is just, what is this distance? It's just x. And then the height is 2x minus x raised to 3 dx. So now this is your formula for the volume. Let me put this at the other side. And then so I think it's better to box this. And then this is your final answer. Put like ans to indicate that it is your answer. All right. Now, let us go to another example. We have the function. So the resulting solid here is, this is your curve and then you revolve it here. So this is something like this. It's like a feeding pot for your dogs. All right. Next, last example before we call it a day. So y is given by x minus x squared. And then r is bounded by x-axis and revolve about x is equal to 2. Now let's draw the region. The region is this one. So x minus x squared is equal to 0. We get x1 minus x equal to 0. X equal to 0 and or x equal to 1. So this is the intersection 0 and 1. And then we revolve this about x equal to 2. Okay, so here is our axis. Now we get a strip. Let's color it blue. And then from the strip, we have a distance from the y-axis. This is x. And then the distance from x is equal to 2 is 2 minus x. Now for the height is just this function. Y is equal to x minus x raised. Now the volume will be 2 pi. And then we'll start from 0. And with 1, r of x, h of x, dx. This is just 2 pi, 0, 1, r of x is 2 minus x. Because this is the distance from the axis to our strip. And then the height is x minus x squared dx. This is your answer now. Okay, so I think this ends our Math 27. I hope I can see you for the final lecture for my class at Math 27 face to face. Thank you for attending and have a great day ahead. So let's go with our goals. We have improper integrals and areas. We have also volumes. So we did all that we planned today. Thank you everyone for watching. I'll now stop recording.